Jackie Wong with the Concrete Materials Testing Branch. We're here outside the Concrete Lab on the docks, and I'm going to show you what we do here in the Concrete Lab first. All right, here we go. We test a variety of things here, from concrete mixes, overlay materials, polyester, methacrylate, all of that. So this lab has been around since the beginning, the 50s. We have a lot of grinders. We need to grind samples or specimens, mix sauce to prep anything. We have a large mixer here. 1.75 cubic feet mixers. So if we want to verify any mix designs for any concrete mixes, then we can do that here. We have the ability to. So we do. We want to mix up any shrinkage bars for concrete. Any other polyesters, we do that here as well. All the polyester magic happens in this corner. Scales, measuring out, aggregate, cement, water, so we can do all of that. It's kind of like a kitchen for concrete. So, and that's just making samples, and then we do a whole variety of testing after that. So, oh, hey Larry! Move it over to Larry to talk about polyester.
One of structure maintenance's main rehab strategies is a polyester overlay, where it's a polymer concrete. The binder, instead of being cement, is a polyester. And this is an example of what a polyester overlay would look like on a bridge deck. The neat thing about this is back in the mid-'80s, either the state of Washington or Oregon were trying to perfect this application, and we actually had a gentleman, Leo Ferroni, who worked here, who was a polymer expert. Washington and Oregon, both their tries were failures, and so Leo took a look at this, changed the gradation, changed the type of polyester, and how it was applied, and it was a success. So we've been using it here in the state of California for 30 plus years, and it's now being used worldwide, and they even have some placed in Sri Lanka. Yeah. And so this is the room where we do all of our compressive strength testing. Structures are accepted based on compressive strength. We get samples from all over the state to test. They come to us in what we call cylinder molds, and they are stripped and cured and broken. This particular press here is a 600,000 pound press, and this press right here is a 400,000 pound press. So we get a compressive strength sample, 6 by 12 inch concrete cylinder. The ends have to be prepped before we break it. We use a sulfur capping compound, which is heated from 265 to 290 degrees Fahrenheit. This will give us the surface requirement that we need. This material dries extremely fast, and it will provide us with the surface requirements that we need. The surface on the cylinder ends have to be planed to within 0.02 of an inch in this 6 inches. So once the capping compound dries, you can see now that surface is nice and flat. So after time of curing for the capping compound, then we actually will break the cylinders. The cylinders are loaded into the press. So we'll load and center the cylinder into the press. So if you want to look at the graph here, we're charting the graph, the strength gain, and what we'll get is a total load in pounds, and then is converted to PSI.
6-inch cylinders are doing compressive strength is daily work. Every single district will have this type of test setup, kind of more or less, to verify good quality assurance on concrete placements. 24,000. So we're past the halfway mark that we think.
So this particular cylinder took a maximum load of 161,319 pounds, which equates to 5,705 psi. And there's what it looks like when you're done. All concrete that we receive, all concrete gets a moist cure, is what they call it. This is not steam, this is just air over water, temperature controlled, and it's a requirement of 95% humidity minimum. So you see these are all of our racks set up for the breaks for the different days that we'll do. So this is through next week. We have an overflow rack for cylinders that are older than 30 days. Sometimes they come to us and there's a 42-day break or 56-day break. So they'll go on the hold rack before they move into the queue to be broken.
Hey Larry, what's this tub for?
This tub over here is for, we would have it filled with water and saturated with lime. It's a requirement for one of the tests to cure concrete beams. They go into lime water 24 hours before we actually break them. And
Or an excellent kiddie pool on hot days. So the Concrete Lab also serves as a bit of a library of things, and we also do a lot of research here. So here are just some old samples of running polyester from different manufacturers. We did some temperature tests to see, you know, how the cure rates and heat of hydration would happen, or heat of gain for polyester when it's a different type of catalyst. We worked with this, which is a hybrid polymer concrete. It's kind of like polyester, but a little less VOCs out there. A wall of shame of not so great samples that we've received with sponges and gloves in them. Some pull-off experiments that we did with UHPC, ultra high performance concrete, and polyester concrete. Here's some more breaks for ultra high performance concrete. So we're talking like 24,000 psi strain. Some samples from some split tensiles, some pavement, some blanks. So we do a lot of prep work. So we have a collection of things ready to go when we want to do certain tests, like slant shears. And then we have a whole history of things that we test here. So here's some cellular concrete, weighs like nothing. That's used for like infill. We've got some other cement treated base. Here's some concrete that we've got fibers in. Old pieces of masonry from some sound walls. So all kinds of stuff. So anything that's in the land of concrete and mixed things, we test here. We have a lot of old stuff. We got a lot of new stuff. So there's just a variety of things. So it's kind of neat. And where the Concrete Lab ends, through these meat curtains, the Cement Lab begins. Here we go. So here, oh hey Ben, our Cement Lab manager. He's going to walk you through some of the stuff we do here at the Cement Lab. Take it away, Ben.
Hello, I'm Ben. I work here at Cement Lab. I'm the MREA, the lead worker. We test cement, which is one of the ingredients in concrete. It is the ingredient that makes everything else work. It's the sticking agent, right? That holds everything together. Okay, so cement is not a hard thing. Cement is a powder, a fine gray, typically powder. And so we get samples of this from our suppliers, and all these materials will come in. They send a sample in once a year. We test it and make sure that it meets spec and all our requirements, as well as the sort of national requirements, the ASTM and AASHTO requirements. So it's cement, and then this is a fly ash, which is the ash, the byproduct of coal burning. It's an ingredient in concrete that Caltrans requires. makes for better concrete. It decreases the porosity of the concrete. It makes the concrete more resistant to something we call ASR, alkali silica reactivity, which is where the alkalis that come from cement react with the sort of glassy elements of certain aggregate and create a gel which absorbs water, which then swells and can crack concrete apart.
Cracks feel good.
Cracks bad, because then everything gets in and things happen that we don't like. So we will, with our stand mixers, fancy KitchenAids, we mix up mortar, which is sand, water, and cement. We make these little cubes. These are our molds, and they make these little cubes, and that's how we test the strength of the cement. They'll be aged in the fog room, which you probably got shown. And we have our own sort of dedicated cube press over there. So that's a strength test. One of the other things we'll do is time of setting, right? So you want to know how long that cement takes to set. So we'll make a paste, which is just cement and water. You kind of push that wet paste. This is a hardened one, but you push that wet paste into this little cone on the thing, and then you have this needle, and you test that every 5 or 10 minutes. And when the needle won't penetrate more than a certain amount, that's initial set. And when it won't penetrate at all, that's final set. So there's a lot of different materials that we can end up testing that fall under the cementitious materials umbrella. Type 2 is a very standard. Type 3 is a finer grind, and so it will set up faster. It may not have a higher strength than the Type 2 in the long run, but it'll get that strength a little faster. Type 2 5s. The 5 has a higher sulfate resistance. I don't know how far I should go into that, but a lot of the 2s also meet 5, and so there's a 2-5 category. 1P or IP is generally a Type 2 that has some pozzolans, and we'll get into that, mixed in with them as a single product, right? It's a mixture of cement and pozzolan. 1L is kind of a new thing. We don't really allow it in our specs yet.
Not yet, but coming online soon.
Okay, which has instead of pozzolan mixed in, it's ground limestone that is intermixed, and that's to help with greenhouse gas emissions, because cement is a big greenhouse gas emitter. Cement production.
Yeah, I would say about 90% of all greenhouse gas emissions for concrete come from the cement alone.
We're the bad boys. Slag is a blast furnace. When they're making metals, there's a product called slag that comes out of that, and it's actually a hydraulic cement in itself. It is often mixed with normal Portland cement for good qualities. What does it do?
It reduces permeability, it binds all the yucky stuff in the concrete that we don't want, and it's a byproduct of a process that already exists.
Okay, so it's
useful.
kind of a waste product that we can get rid of. As well as fly ash, which I've shown you there, and again, that's a byproduct of the coal burning. Again, it's a waste product, and it's kind of a good way to get rid of it. But not all fly ash meets our quality needs, and so some of it is used and some of it, there are types that are not. Silica fume is a byproduct of the silicon chip making industry. It's extremely fine. It's basically like silica particles that are fine as smoke, and again fills in the matrix of the cement and concrete that it just blocks those tiny pores. So pozzolans, if I mentioned that word, are a group of things that react with the alkalis in cement in this positive way that increases the quality of the concrete. One of the other things we test cement for is fineness, right? How finely is it ground? And so we have a couple of different tests for that. This one we call the Blaine. That's the equipment name. This is the Blaine device. You take a very specific amount of cement, you put it into this cell with some filter paper, you compress it to a certain volume, and so it should have a certain porosity at that point. You put this whole cell up here, you pump this right in. Right? And then as this liquid falls back down to its own level, it's pulling a small amount of air through that little pellet of cement. And the finer the cement, the more difficult it is for the air to sort of find its way through all those particles. And so it'll take longer. So you're timing how long this takes to return to its level point. And that is an indicator of the fineness.
Okay, and this is our 50% humidity room where we will store specimens that require 50% humidity. So in my hand is, for example, a shrinkage bar for concrete when we need to test and verify shrinkage. Follow me in. And we also do this for mortar bars in the cement lab. We will do equilibrium density when we're trying to do weights for like a lightweight concrete. And here also we have our creep racks. So if we need to do any creep testing for like long span bridges, we can do that too here. We did a lot of that in the late 90s and early 2000s for the Bay Bridge. And if we come out, follow me. So when we're measuring or getting our readings every week, this is how they're done. And that's it. And that's what the purpose of the room is. So we can maintain 50% humidity and keep specimens at a constant environment.